Welcome back to another episode of Dave Does Math from Home. We are doing more double integrals. This is the start of a new section about double integrals, and I'm not going to waste any time. I just want to do this double integral right here. What we have here, I've already got it written down. What we have here is a paraboloid. This is the function z equals x squared plus y squared. We played with those a little bit in chapter 15. It's like a bowl shape. It's like a three-dimensional bowl paraboloid that goes up like this. So I want to find the volume beneath this paraboloid. These bounds, y is going from negative root 9 minus x squared to positive root 9 minus x squared. Hopefully we can all recognize this as the circle of radius 3. If you square both sides of this equation and move the x over, you have x squared plus y squared equals 9. So this is our circle of radius 3, and of course x is going from negative 3 to positive 3 because this is our circle of radius 3. So I have a very round shape, a nice round paraboloid. I'm finding the volume beneath this round shape in a circle. So I have a round function and a round region, and we're going to do this using dx and dy rectangular coordinates. Let's get started. dy is our first integral, so when we integrate this, we're going from negative 3 to 3. These are x values. The integral of this with respect to x is going to be x squared y plus 1/3 y cubed, and this is getting evaluated at negative radical 9 minus x squared up to radical 9 minus x squared, and these are still y values, dx. So when I plug these guys in here, I'm still going from x is negative 3 to x is 3. I have x squared times the square root of 9 minus x squared plus 1/3 9 minus x squared to the 3 halves. This is what happens when you take the square root cubed. It gives you the 3 halves in here. Minus, so it's going to be minus negative all this. So I feel like I can save myself some simplification. Instead of doing this all again with a negative sign, 2 negative signs involved, I'm just going to double the whole thing. So at this point, we have to integrate x squared times the square root of 9 minus x squared, which looks like it should be some kind of inside outside other business, but I can already see that it's not going to work. And here we need to integrate 9 minus x squared to the 3 halves power, which is definitely some kind of composite inside outside other function, but there is no other function multiplying this piece at all, so that is definitely not going to work in any reasonable capacity, and we are going to be really sad about it. The moral of this story is, when you integrate round things using square coordinate systems, it is at best really, really disgustingly messy, and at worst it's completely impossible. Like this. We can't finish this. We do not possess the analytical technique required to finish this integral. It's just not a thing that we can do, which kind of sucks. But there's good news. We can do this integral. We just have to use round things. This integral is a round surface over a round region. Doing this with using rectangles is a huge mistake. We can do this using other coordinate systems that are round, and then the roundness of the function and the roundness of our region and the roundness of our coordinate systems will complement each other, and they will make this incredibly effortlessly easy. That's the goal, and that's why this section is called Double Integrals in Polar Coordinates. This is part 1. So, I hope you all remember polar. We're going for it. I'm going to leave this integral here for now. I'm just going to destroy the hard work we put into it that led us nowhere. Let's talk about polar coordinates so that we all remember approximately what we're doing there. In a rectangular coordinate system where this is x and this is y, if we're looking at a point like 2, 3, that means 2 units right and 3 units up. These things are called rectangular because it's all 90-degree angles. Sometimes it's called Cartesian because it was developed by a guy named René Descartes, who was a French philosopher and mathematician. If we want to do polar coordinates, instead of describing positions using orthogonal distances, we're going to describe our position using an angle of elevation off of the positive x-axis. I guess I shouldn't say elevation. An angle of direction. Yeah. An angle on the xy axis and a distance. So this is polar. And there are some equations that I'm confident we all remember from pre-calculus that connect polar and rectangular functions and coordinates. The relevant equations are x is r cosine theta, y is r sine theta. That comes very directly from the triangle that you can make in polar coordinates. Since the angle is always with the x-axis, this is always the adjacent side. This is always the opposite side. So your x is the adjacent over the sine of this is adjacent over r, and that's your x. Or cosine is adjacent over r, that's x. Sine is opposite over r, that's y. That's just your basic triangle trig. Pythagorean theorem can be of some assistance here. The triangle also gives us x squared plus y squared equals r squared. This is going to be extremely useful for us. Maybe you can already tell how. And we're going to use maybe we won't use this one as much, but the tangent of theta equals y over x. This one probably won't come up much, but I'm going to include it anyway just so that I can have the full set. These are the important transformations. This is how we transform things from rectangular into polar and polar into rectangular. For example, this thing that we have right here, this is a rectangular function. This is being given to us in rectangular coordinates, x squared plus y squared. We can transform this into a polar function pretty effortlessly. X squared plus y squared is just r squared. That's the function. This function we're integrating, z equals x squared plus y squared. In polar coordinates, that's just z equals r squared. Which makes sense, because this is, r is your distance away from the origin. And if you have something that's a parabola, but in a circle, like a paraboloid, that's just, if you start at the origin and walk in any direction, the distance r you go out needs to match that parabola curve. So z equals r squared. It's just a round version of y equals x squared of our standard issue two-dimensional parabola on the xy plane. So we have a new function. That's nice. That's going to be very helpful for us. We need new bounds if we're going to do this in polar coordinates. And these bounds are actually going to be extremely easy for us. These bounds as written described for us a circle of radius 3. So if we want if we want to use polar coordinates to describe a circle of radius 3, 1, 2, 3, using r and theta, this is extremely straightforward. This region is incredibly easy in polar coordinates. R goes from 0 to 3. It does this the whole span of that. R starts at 0, R goes out to 3. That's that space. Theta goes from 0 to 2 pi. It's going all the way around the circle. So if theta goes all the way around the circle, and r goes all the way in between 0 and 3, that gives us the circle of radius 3. So when we finish this integral, we'll have a dr and a d theta. And r is going from 0 to 3. And theta is going from 0 to 2 pi. So our function got much easier. Our region got expressed much, much, much easier. This is the big draw of polar coordinates, is that when you're trying to express a round region in rectangular coordinates, these square roots are going to get involved and they're going to make a colossal mess of things. Like what we started this video with an integral that we couldn't finish because that's how severely these square roots made a mess of things. In polar, not only are there no square roots involved, but they're constants. We're back to having constants as our bounds. When we started chapter 16, we were doing double integrals over rectangles, because rectangles are what you get when you only ever put constants in for your bounds. It makes these nice square right angle regions, no weirdness, no curves, no slants, just a rectangle right in the middle of the xy plane. It's very convenient because they're constants, and those are really easy to evaluate. Circles are the same thing in polar coordinates. You can always express a circular region using constants here, and that's very, very nice. There is, I'm going to talk more about bounds later, so don't think I'm done with that. I just want to finish this particular integral. And the way I'm going to finish this particular integral is with there's kind of a weird thing, weird non-intuitive part of these polar integrals. It takes a little bit of getting used to. When we did double integrals, we had our tiny little chunk of the x-axis, and we called that dx. And we had a tiny, tiny little chunk of the y-axis, and we called that dy. And we said this little box in the middle, this is our area. The book calls it dA. The little tiny piece of area, because it's a little rectangle on the xy plane. Dx is its width, dy is its height. That gives us a tiny little box that has an area, and we call that area dA sometimes. Here's what's really awkward about this. We need this to give us an area, but it kind of doesn't. Not yet. So if we think about what dr and d theta mean on this plane, d theta is a tiny, tiny, tiny little slice of angle, and dr is a tiny, tiny, tiny little slice of radius. So this is dr, and this is d theta, and it gives us sort of this arc shape, this segment, like the pizza crust. like if this is your pizza slice, this is where the toppings go. This is like your pizza crust. It's a round sort of bar. There's two problems with this round bar as a measure of angle. The first problem with this round bar is that dr and d theta have a varying size. The nice thing about dx and dy is that it doesn't matter where you put the dx and it doesn't matter where you put the dy. As long as those things are tiny little chunks of axis, they're going to give you the same sized little chunks of area on the coordinate plane. This will give us bigger chunks the farther away you go and smaller chunks the closer to the origin you are. If you have like a 30-inch pizza, you're gonna have really long slices of pizza crust. If you have a tiny, tiny, tiny pizza, your slices of pizza crust will be small. They will be short. There just won't be much. I mean, assuming you're cutting the pizzas into the same number of slices. If you cut a personal pizza into 8 slices, your crusts will be very small. And if you cut a huge party pizza into 8 slices, you're going to have crusts that are longer than your hand. And that's what's going on here. These things grow in size the farther away from the origin you get. And so we need some way to reflect that. We need something that's going to tell us that these things are bigger when they're farther away. These chunks of area that we have are bigger the farther away you are. The other problem we have is that it's a problem of dimensions. If x and y are being measured in inches or feet, that means that dx and dy, as changes in those things, so if x is in feet, then dx is a change in that, which is also measured in feet. And if y is measured in feet, then dy is a change in y, and that's also measured in feet. So when you multiply dx and dy together, you're literally getting a measure of area. Like, if x and y are both feet, then the expression dx dy has units feet squared. And that's why I keep on saying that it's a measure of area. Dr d theta only has one physical dimension to it. Radians are unitless. R could be measured in like feet or inches or miles or whatever unit you want to use to measure R. That's a measure of distance. And so dr has that measurement. It could be, you know, feet or inches or miles or meters or centimeters. This has a unit of length attached to it. This does not. So there's two problems we need to solve here. One is that simply multiplying these two things leaves us lacking in a dimension, lacking in a unit. If we want this to represent an area, we need it to be measured in like feet squared, inches squared, something. It needs to have two units involved, units squared, and right now we just have unit. And we need to represent that it gets bigger the farther out you go. And the extremely elegant solution to both of these problems is that r dr d theta is our new dA, which is going to take some getting used to. We're really, really used to just putting a function here. Here's your function. We're done with the function. On the back end, you staple a dy and a dx on the back end of it, and that's your order of integration, and that doesn't really do much. Here, the things you staple to the end of your integral include a variable that is going to mix with the function. These things are going to combine, so we're not actually going to be integrating r squared here. Ultimately, we're going to integrate r cubed, because our dA comes with an r attached. In class, I promised that this was the section of pirate integrals, and it is the section of pirate integrals because the easiest way you can remember that you always need to do r dr d theta is to just talk like a pirate. R dr d theta. These jokes write themselves. I can't make this up. Pirate integrals. R d theta. These get attached all the time, every time. Don't forget the R. Oh god, we're at 20 minutes already. Okay. Part 2 is going to be me evaluating this integral. Stay tuned.